Okay, so let's go ahead and prove Cauchy's theorem. Let's just remind ourselves quickly what it said. Suppose f is analytic in a simply connected domain in D, and that f prime is continuous in D. Then for every simple closed contour C in D, the integral, well, the contour integral of f over that contour is 0. All right, proof. Well, suppose that f is analytic, and we don't need this second assumption, but I'm going to put it anyways. F prime is continuous in a simply connected domain D. All right. Then what? Well, the contour integral of f dz is, let's write f is u plus iv. So this is going to be the contour integral of c of u plus iv. And then dz is dx plus I dy. So that's going to be the integral over c of, let's see, I think we're going to get u dx minus v dy plus u I dy plus iv dx, which we can break up because integration is linear, and also factor out the I, integral over c u dy plus v dx. Now since f prime is continuous and our domain is simply connected, the contour, let me draw the C over here, C bounds a region R that is entirely within D. So this is all within D. Namely, the derivative of our functions, and our functions are defined here. So u, v, ux, uy, vx, vy are defined here on R, and they're continuous. Sometimes continuous is written C0. All right, so that's the crucial part. And once you know that, then you can always transform your integral, your contour integral, to an integral over the region using Green's theorem. So by Green's theorem, oh shoot, I missed a golden opportunity. By Green's theorem, this integral is going to be the double integral over R. And what do? Let me put maybe Green's theorem a little bit lower here. Green's theorem tells us that if we want to integrate over a contour p dx plus q dy, we saw this a little bit ago, that's the double integral over the region qx minus py dA. So here p is u and q is negative v. So I'm going to get negative vx minus uy dA plus I times the double integral over r. Okay, so in this case, q is u and p is v. So I'm going to get u x minus vy dA. All right, but f is analytic. So far, the only thing we've used is that f has the real and imaginary part of f have partial derivatives that are continuous, and we've used that the domain is simply connected to see that all of them are defined in the interior of C. We haven't really used analytic yet, and we're going to use it now. So the Cauchy-Riemann equations hold. In particular, this tells us that ux is vy, or equivalently, ux minus vy is 0. And it tells us that uy is negative vx, or equivalently, 0 is negative vx minus uy. So in particular, if we were to go back up to our computation here, that's 0, that's 0. So what do we get? Well, we get 0. That's it. Proof is over. So that's the proof of Cauchy's theorem. And the condition that f prime is continuous, again, is irrelevant. So we have the modified theorem that I'll state now. This is called the Cauchy-Goursat theorem, which relaxes that second condition. So what does it say? Let me use my pink here for a second. It says, suppose f is analytic in a simply connected domain, then for every simple closed contour, in D, contour C and D, the integral over C of f is 0. So we don't need that analytic, the continuity of the derivative.